it to you.
Good.
Yeah.
So I started recording. Thank you. So I'm going to tell you about a recent progress in algorithms for independent set and similar problems, but that's only at the end and very vaguely, on PT3 graphs and related graph classes. And there's like the title says we are shrinking the space of induced subgraphs because in the last years we were not the first ones to have. I mean, there's a group at UCSB who gave the first quasi-polynomial-time algorithm for independent set in PT3 graphs. And our observation, our main contribution here, which I'll be talking about, is like to simplify the algorithm and to understand better what it's really doing and get a better running time bound with a much simpler analysis of what's going on there. And this is joint work with Michał and Paweł. At the very end, there will be like more people joining the group as I will progress during the talk, but at the beginning, it's just us three. Okay. So let us start with some motivation here. So yeah, so we study, in some sense, we study like in a methodological fashion how restricting graphs, like the family of graphs you're studying, how restricting the family of graphs you're studying impact the complexity of some problems. So yeah, so for example, some problems on planar graphs is simpler, or some problems on trees is simpler, but I mean, there's like a lot of different graph classes, and one of the methodological, or like one of the like organized way of studying them is to look like which forbidden induced subgraphs, because essentially every reasonable graph class you will think about is closed under vertex deletion. So you think about hereditary graph class, closed under vertex deletion, and then you think, okay, which guys you forbid as induced subgraphs, and then you get like a more tractable class, or a class where more problems are solved efficiently. And if you start to do it organized, if you start thinking in these terms, one of the ways is to forbid one graph, like H3, look at the graph forbidding one fixed induced subgraph, and then think, okay, what's the property of this graph class out there? Okay. And it turns out, I mean, if you just think of graph classes closed under vertex deletion, I mean, planar graphs are closed under vertex deletion, but also like many graphs you hear in graph theory, like perfect graphs, line graphs, Corzer graphs, many other things are closed under vertex deletion. So essentially every reasonable graph class is closed under vertex deletion, with some few exceptions. And yeah, but we here look like to have like an ordered, organized way of discussing which graph classes are hard, which graph classes are easy. We think of like forbidding one forbidden induced subgraphs and see how it changes the complexity of some problem. So for example, in this paper, we forbid a path. I mean, one of our heroes is forbidding an induced path. This is an induced path in a graph. So this is an induced path on 6 vertices called P6. This one doesn't have got an induced path on 6 vertices. It has a path on 6 vertices, but it's not the induced one. There are some edges, extra edges apart from the edges of the path. And this one has got the induced path. I mean, there are no extra edges here in this red part. Okay, so that was meant to be H3. That means that there's no H as induced subgraph here. Okay, so this is the setting we have. And we are going to solve the minimum weight independence set problem, which is probably one of the most known NP hard problems, like sometimes easiest, sometimes the most important NP hard problems. And the weight thing says that actually, yeah, the weight thing is that I mean, the weights are like just to like make something harder, but also to make it more general and to be able to encode some other problems inside the maximum weight independence setting. Okay, so this is the problem we are going to study. At the very end, I will tell more about other problems here, but this is the main hero for like 95% of the talk today. Okay, and yeah, so this is the solution here. It's not largest in terms of cardinality, but this is the heaviest one because I mean, this is just weight 4. Okay, so what do we know about maximum weight independence in H3 graphs? So in arbitrary graphs, this is an NP hard problem that everybody knows after the algorithmic course or whatever course you were going to for complexity theory and NP hardness. But yeah, but there was observed like there's an observation that if you subdivide an edge twice, the problem essentially doesn't change. It just increases the size by 1. I mean, if you look at the unweighted version. So if H contains a cycle, this problem is still NP hard, because if you subdivide every edge enough times, the shorter cycle in a graph becomes very long, and the problem stays essentially the same. And also there's a, I mean, K14, I mean, it's NP hard in graphs of maximum degree 3, and from that you can, and the previous trick, you can get that actually if H has a component that's a tree with more than 3 leaves, then actually it's already NP hard. Yeah, so I mean, for H3 graphs, maximum weight independence set becomes hard, becomes NP hard for most of H, and what's left are really paths close, like subdivided and subdivisions close. So like like graphs looking like this. There can be many vertices here. This is subdivided claw, and like forest of those, so that you can have like like disjoint union of a number of them. And for that one, the NP hardness proves we have breakdown. And this is actually it, in the sense that, okay, at this moment, we don't have any more NP hardness results. I mean, uh, for all we know, it can be polynomial in any PT-free graph or like claw-free graph or like subdivided claw-free or like 5 subdivided claw-free graphs. It can be as well polynomial, and that's like what and that we found interesting. I mean, that's this from the point of like graph classes. It's interesting. That's quite a lot of quite complicated graph classes like P100 free graphs, where we don't know maximum weight independence to be NP hard. And the same situation happens for free coloring, for feedback vertex set, and for I don't know if all I think also Osaka transversal as well. So this is like there's a bunch of problems somewhat close to maximum weight independent set that we don't know how to make NP hardness without creating a long induced path or long induced subdivided claw in the gadgets. Okay. But on the polynomial side, the progress is also like quite limited. Like if you want polynomial time algorithm, like if you exclude P4, these are cographs, and this is like the ancient Greeks knew how to solve it. But then we needed to wait until like 6 years ago before P5 free graphs were known to be polynomial, and then we hammered the technique used for P5 free graphs for a while until we get P6 free graphs that was published on Soda like 2 years ago. Okay, so this is P6 free graphs, and that's it. And the technique that was put for P5 and P6 free graphs actually, like in a sense, has good exponential complexity of case analysis, and we don't expect it to work really for P7 free graphs unless we have got really good new ideas. Meanwhile, somebody observed that, I mean, a few people observed that, two independent people observed that claw-free graphs, in claw-free graphs, it's essentially it's not the same algorithm, but you can use all the intuition from maximum matching algorithm or all the knowledge from maximum matching algorithm to find maximum weight independence in claw-free graphs, because like there's a notion of augmenting path there as well. And then there's a paper of Łozin and Milanic from 12 years ago that if you subdivide one H1s of this claw, it's still polynomial. But just in this paper, really say, I mean, the essence of the paper is that fork-free graphs are not that more complicated than claw-free graphs. I mean, there's like, yeah. And we have a paper on this Soda with, there's this 5 should be actually below, with people from Princeton, Pavel, that actually if you look at C at least 5 free graphs, what does C more than 5, which means that no, this should be more than 4 actually. Okay, I will just put C more than 4. Yeah, so this should be like I forbid a cyclone 5 vertices, I forbid cyclone 6 vertices, etc. Yeah, so I forbid C5, C6, and all the graph up there. Yeah, so it's not a single forbidden subgraph, induced forbidden subgraph, but a lot, an infinite family of them. And note that, so I will denote in the C equals C less than 10. That means that I forbid CT plus 1, CT plus 2, etc. So I forbid all induced cycles of length more than t, and note that PT3 graphs, if a graph is PT3, it's also C more than T3. Yeah, because every long enough cycle contains a long enough path. Okay, so yeah, so actually we show the polynomial time algorithm for like C at least for C at least 4. Actually, it's also like it's a bit wider class than C at least 4. It actually contains the P5 free graphs as well. So this is like a generalization of the P5 free graphs. It's slightly more general. I mean, C at least 4 it doesn't contain P5 free graphs, but we have got a bit more than that, and I mean a bit wider class that also includes P5 free graphs. Okay, so that's the polynomial, and it seems a bit stuck. Yeah, it seems a bit stuck. And so maybe we should relax the question of whether we want a polynomial time algorithm. Yeah. So yeah. So we know that P6, P4, and there's also this C at least 4 here that I didn't copy here. Yeah. But let's try to relax the polynomial time algorithm. Let's try to get something weaker there. And there's simple there. I will just do it in 20 minutes. there's a paper we had in a large group at IPEC a few years back that said that, okay, in general graphs, there's an ETH lower bound that you cannot get sub-exponential, but on PT3 graphs, you can actually very easily get sub-exponential. And that's like, it will be like in a few slides, it will be two-liner once we learned enough about PT3 graphs. Okay, so this is like a sub-exponential algorithm. And then we had the paper on Soda actually like less than a year ago that says that there's actually a Cupitas. And this Cupitas, what's important, this Cupitas also works for subdivided flow-free. Yeah, so it also works for the subdivided flow-free graphs. So it's not only works for PT3 graphs, but also for subdivided flow-free graphs. And for PT3 graphs, it's actually relatively simple. For subdivided flow-free graphs, the thing starts to happen there. Okay, so this is really we have a Cupitas there. So that means that problem already becomes a bit easier, yeah? Because maximum weight independent set has got like some horrendous hardness, approximation hardness results, like no n to the 1 minus epsilon approximation for unweighted version, okay, in polynomial time. Yep. And now this Fox, and this appeared somewhere in May on arXiv, the team from UCSB, Peter Gartan and Daniel Lokshanov, announced a quasi-polynomial-time algorithm. And this is like the first result that really says, hey, we don't think this is NP-hard. Yeah, because you can have an NP-hard problem with a Cupitas. You can have an NP-hard problem with a sub-exponential algorithm, but you shouldn't have an NP-hard problem with a quasi-polynomial-time algorithm. Yeah, so they published this one, and this naturally gets accepted to Fox. And yeah, and we looked at their algorithm, and what we had accepted to SOSA in January next year is slightly faster, so 1 log less, and arguably simpler algorithm. I hope to present the entire algorithm to you in a few slides. And this is like, SOSA is quite a new conference, symposium on simplicity algorithms. So it's supposed to have simple, clean, beautiful algorithm. I don't know how beautiful it is, but I think it's simple. Okay, so this is like the recent progress we have. And like, okay, so this is it. And I'm going to speak mostly about this result. There will be like some conclusion slide at the end about extensions, but this is the result I'm going to show you, and I'm going to prove to you in like the next 20 minutes. Maybe more, maybe less. Do you have any questions now? Because I will slowly go to technical part.
No so I have only one remark. I think on previous slide you also mentioned the odd cycle transversal problem, and I think it is actually NP-hard in some PT3 graphs.
That may be true, because I was confused for a moment. Admittedly, the slides, I think odd cycle transversal has got some P5 or P6 being open, and then it starts being hard in some moment. I got confused, I didn't check it. Admittedly, this is like this introduction slides, this is like a 4th or 5th edition of the same slides from various talks. So maybe I
yeah. The situation is in OCT, as far as I remember, it's hard on P6-free. It's easy on P4-free because it's co-graphs. And on P5-free, we had a sub-exponential algorithm on this ESA. It's open whether it's polynomial on P5-free OCT.
Mm-hmm. Yeah. Okay. Thanks for the remarks, and I think, yeah, sorry for this confusion there. This is like the P5-free. It should really disappear from the slide. Only the P5-free here is open, so it's not really fitting the scheme that like for arbitrarity is the problem. So okay, forget about odd cycle transversal. I'm sorry for that. Good. So let me go further and let me look at what's the main tool there. So the main tool is the argument called drFash path, and this is something Michał already presented, because if you remember, and if you were attending seminars so far, we may have noticed that actually Michał was talking a few months ago about the Cupitas result up there. Yeah, and Michał used something called drFash path. I'm going to recall you what's going on there. This is like really drFash path along back, but drFash used it to prove chi-boundedness on PT3 graphs, so he used a bit different setting. Then in this setting, I will show you for PT3 graphs, it was used by us in this sub-exponential algorithm, and then the context of C at least T3 graphs, that was really like the exact statement that appears in this Cupitas paper. But essentially, this like all combinatorial ideas come from drFash. It's just adjusting to the rest is just adjusting to the correct setting or understanding what's exactly needed from this combinatorial argument. Okay, and what does it really say is that, okay, if we have a graph, okay, which is like C at least T3 or think PT3, then there's actually some set here, which is small. Oh, I should have of size at most K, yes. So it's really at most T, which is connected. And if you take the neighborhood of the set, and you delete it, then the rest gets balancedly separated. So if you take A to be the entire vertex set, that means that you actually split the graph into connected components of size at most half, which is excellent for some recursion or whatever. Whereas I phrased it in this way so that you can actually think of like putting weights on vertices and splitting the weight up into like multiplicatively smaller pieces. Yeah. So what does it really say? It says that a PT3 or C at least T3 graph contains a balanced separator, which is a union of T neighborhoods. And this is like connected, like these neighborhoods are connected actually in a path, but we'll see in a moment. Doesn't really matter for applications, it's a path. Okay, so this is the theorem. I will prove it in a moment on a notebook, but before I do it, let me just get the sub-exponential algorithm using it. Okay, so recall that we have got there's an algorithm which is like roughly 2 to the root n. If you think of t being a constant, I mean, there's like some logs or something like that appearing, which we don't care much. Well, the point is that maximum weight independent set has got this very natural heuristic, I mean, very natural brute force algorithm for branching. So what you do, you take one vertex, yeah, and you say either it's not in your solution and then you delete it, or it's in your solution and then you delete its entire neighborhood, and maybe you just put it, you can delete it and then just include it. Okay, so you have got a vertex, and if this vertex is in the independent set, then none of his neighbors can be, and if it's not, then we just delete V. Yeah. So we have got this branching, which is like, hey, I delete a vertex or I delete its entire neighborhood. And the intuition of this branching is that you want to pick this vertex to be like a central vertex in the graph, so that, okay, maybe you will not delete, there's a branch when you delete only one vertex, but there's this super nice branch where you delete the entire neighborhood, and maybe you make a lot of progress. A lot of parts from the graphs get deleted. Okay, so this is like the very like high level overview of the algorithm, I would say. So take a vertex and branch, and whenever you get into different connected components, whenever they're like, whenever you split into, I mean, and you can also split between, if you get disconnected, you can independently treat connected components. Okay, so this is like general toolbox what you can do with PT3 graph, with graphs and maximum weight independent set. The observation of the paper of the algorithm of Bacho et al. Is that if there's a vertex of degree roughly root n, or at least root n, then branching on this vertex gives a sub-exponential time algorithm. Yeah, I mean, this is a sub-exponential time recursion, because in one branch you delete one. In one branch you delete one vertex, but in the other branch you delete root n vertices. Okay, because you delete the entire neighborhood, and this recursion solves to like n to the order of root n. Yeah, this recursion solves something like that. Okay, so I mean, there's some balancing out with this log and whatever here, but this is like the intuition. If there's a vertex of degree more than root n, then branching on it gives a recursion which has got sub-exponential running time in the end. Okay, otherwise, if there's nothing like that, then this balanced separator thing can be iterated, or like can be bootstrapped to actually get a tree decomposition of width, roughly like the size of these neighborhoods. Yeah, you can do balance separator, then balance separator, blah, blah, blah. I mean, there's like a standard thing that if you have got a method of finding small balance separators, you have a method of finding a narrow tree decomposition. So otherwise, there's a tree decomposition where every bug is essentially T neighborhoods, or like order of T neighborhoods. Okay, and so that means like the bug size is T root n or something like that. And here, what's told here is really that if you can balance out this T and log n somewhere inside the root, so to get this running time bound. Yeah. So if there's a vertex of high degree, high meaning more than root n, branching on it gives this recursion. Otherwise, the balance separator theorem says that the tree is root n, and you can do dynamic programming on tree in times 2 to the root n. Okay, so that's the algorithm of Bacho et al. That's nothing special, but it's the first application of like the easiest application of this lemma. A bit more involved was for the Cupitas, and actually Michał presented it in a few months back. So that was on the seminar, you should have known it. And yeah, so what I'm going to do now is that I'm going now to first recall how does this argument works, because I think this is like a very nice argument that's very important for everything we're doing here, and then go to the our algorithm. Are you fine?
I'm sorry, but I got a bit lost. So what have we done, and what are we going to do now?
We proved this.
Okay, and now?
We said that this was on seminar by Michał half a year ago. Now we are going to prove this and then do the quasi-polynomial-time algorithm we have with Michał and Paweł.
Okay, thanks.
Good. Okay, so now I'm going to change from slides to the notepad. Yep, and now I'm going to do this. Yeah, so I have got a graph G. Let's start with a graph G. Let's say that this graph is PT3. Okay, and I think of A being the entire vertex set, so I want to split the vertices in a balanced way. The argument stays the same if I put any weights on the vertices, just like more black, so I want to skip this black about weights. Okay, so I want to split the vertices. The graph G may be disconnected, so there are some connected components, and there's like maybe a large one. Okay, maybe, I mean, if there's all connected components of size less than half of the graph, I'm already done. I don't need to take anything. So maybe there's one connected component which is like more than half of the vertices. Okay, pick. I mean, let me draw this component. Let me wipe out this component, and let me draw it large. So maybe there's a large connected component. Okay, pick a vertex in this component, some V0 in this component. Okay, so this is large connected component of size n per half. Okay, and say, okay, I mean, I'm allowed to delete like t neighborhoods in a row. I mean, connected t neighborhoods. Okay, so let's delete this neighborhood. So this is the neighborhood of V0. Okay, I deleted the neighborhood of V0. Okay, good. So maybe, I mean, I deleted the neighborhood. So maybe everything here split into some connected components. Okay, so maybe I will just use a different color, and maybe the rest split into connected components. Okay, if now the connected components after deleting this neighborhood is everybody is smaller than half, I'm happy. I already done. I used one neighborhood. Okay, that's fine. But now maybe there's another component which is more than half. Okay, now because it was connected at the beginning, I can take a vertex here, which is a neighbor V1, which is a neighbor here that actually has some neighbors in this big connected component. Yeah, because I have got everything this thing was connected, this box was connected to start from. I deleted neighborhood of V0. And there's one connected component of what remains here, which is larger than a half. So I could take a neighbor going into, like, it has a neighbor inside this big component. Okay, good. So maybe deleting V0 and V1 helps. Okay, so let's delete also the neighborhood of V1 inside this component here, or actually it deletes more, but it doesn't matter. Yeah, let's delete the neighborhood of V1. Okay, and change the color again. And now maybe here this one splits into connected components. Okay, this one splits into connected components. I deleted two neighborhoods, so maybe already everybody is less than half. If yes, then I'm done. Otherwise, there may be another component of size more than half. Okay, but again, I deleted this blue component was there. I deleted this part here, and I did this part here, and it broke into smaller connected components. But one is still large. That means that I can choose here V2, which has got again some neighbors in this large component, and I can iterate it. And the point is that and then choose the red color. It splits into components. And at some moment I stop. I mean, I stop. Okay, and some moment I stop. I mean, the things in front of me, I mean, the components in front of me have got size less than a half. Okay, so this is some process which is like well defined. All the time I go like take the component which is of size more than a half and like take the next vertex in this direction. The main observation is that what I built here, if I go back, if I take now yellow color, what I built here, this is an induced path. Yeah, because I deleted the neighborhood of V0, took V1, then deleted neighborhood of V1, took V2 there, and the rest is in the next component. So this is really an induced path what I'm doing here, which means that in PT3 graphs, if I go back now take black color, in PT3 graphs, I cannot take t steps. I cannot build the induced t path. After t steps, after less than t steps, this process ends. Okay, after less this step process, and this process is really like deleting the neighborhoods of vertices on a path, okay, and seeing whether there's still a connected component of size more than a half. And I proved the lemma for PT3 graphs. Yeah, I was building a path, an induced path, and deleting the neighborhood, and the neighborhood of this path splits the graph into pieces of size less than a half. And in PT3 graphs, I cannot build and in PT3 graphs, I cannot build a path longer than t, or can't be a path on t vertices. So it needs to stop here. In a sense, I run out of colors after less than t steps here in this process. So I proved the lemma for PT3 graphs. For I'm going down. For CT3 graphs, you need one extra trick. So you start with this V0 and you build this path. And this path can be very, very long because you no longer exclude a long path. So this is this path, and at some moment it stopped so that it has got less than a half in front of it. Okay, it stopped. And for C more than T graphs, free graphs, the main observation is that, okay, let's take, I know, T consecutive vertices on this path. T consecutive vertices on this path, and let's delete their neighborhood. So let's delete the neighborhood of this T vertices, but keep the next vertex on the path. So there's like, I would take a purple color, and there's like the next vertex on the path. This one gets not deleted. So we deleted the neighborhood of the T vertices, except for the previous and next vertex on the path. Yeah. And the point is that now this guy is in some connected component with this part of path. This guy is in some connected component with this part of the path, and this cannot be the same connected component. There cannot be any connection here. Yeah, because if this is a connection, then there's actually a long cycle, an induced cycle of longer than t, because it gets t steps here and needs to close back. So there's an induced cycle of length longer than t. So these are two connected components. So now what you do, you take this green area and you slide it from like left to right, and you look for a position when the thing is balanced, when the component before and the component after this is like a balanced separation. I mean, there's some details to check that there's this position, there's no like extremal part, like at the beginning or at the end. So there's like a few details I'm sweeping under the rug here, but this is like the idea for CT3 graphs. Okay, see at least T3 graphs. Okay, so I proved the theorem about the balance separator. That was the Djarfash path argument. Okay, the original argument of Djarfash proves essentially in the same way, but using different words about like large, what does mean to be large component, that CT3 graphs are k-bounded. Good. So now I'm going to use this argument to get a quasi-polynomial-time algorithm. Okay. Are you fine? Are we fine? Or can I proceed? Good. I am
fine. Yeah.
Yeah, but you're a co-author, so you count.
I am fine too.
Good. Okay, so let's just do the quasi-polynomial-time algorithm. The intuition is as follows. Okay, so what I want to do, how the algorithm will look like. Let's try to do the naive algorithm. Yeah? Let's try to do recursive algorithm to find maximum weight independent set that gets some graph G, and it says the following: like if G is empty, then say 0. Okay, if G is disconnected, yeah, if G is disconnected, then return the sum over connected components. Yeah, split into connected components independently. Else, choose some V, call the pivot, and branch and return the better option of like not taking V, maximum weight independent set of G minus V, and the weight of V okay. So like I wrote a very stupid algorithm. I mean, I didn't do anything wise here. I just wrote the recursive algorithm I'm going to study. Now it's that, okay, if graph is empty, I mean, the maximum weight independent set is trivial. If graph is disconnected, then return, then like split into connected components. Otherwise, choose one vertex and branch on it. Okay, this is exactly the algorithm of Bacho et al. But here they choose the high degree vertex, and at some moment they decided it's not exactly the Baccio et al. Algorithm. They choose the high degree vertex, the Baccio et al. Choose the high degree and fall back to true if the true becomes small. Okay, that was really up there. And now this will be our algorithm. I mean, this will be our algorithm. The only point will be that this thing will put in pink, and this will be like super important. I mean, we'll be choosing V in a very important way, and we'll show that there's actually a choice of the pivot that gives you quasi-polynomial-time algorithm, period. There won't be any hacks on top of this algorithm. Maybe there's some hack like, okay, maybe this one will be like constant size. Okay, for constant size graphs, maybe what I will say won't make sense for some corner conditions, so maybe you need to solve by hand like one vertex graph or two vertex graphs. It doesn't matter, okay? So this is what I'm going to say. And now, so I'm going to show a quasi-polynomial-time algorithm. And the key idea is to actually measure, like have a very special way of measuring the progress, okay? And the idea is as follows. Let's look at two vertices. So this is the graph, we look at two vertices, and we define BUV to be like the family of all induced paths, all induced UV paths. Okay, so there are like some induced paths between U and V. Okay, good. So this is like the family. I will call it the bucket. So this is a bucket. They're all induced UV paths. Okay, and the idea, the intuition of the branching is that I don't really want to like delete in the Baccio algorithm. The high degree vertex was just deleting a lot of vertices from the graph. Okay, here I want to choose pivots so that I disconnect the graphs. If you think about like this T-vertex path, whose neighborhood is a balanced separator, then vertices on this path seem like decent branching pivots, because in case you actually, in this branch, success branch, when you actually take the entire neighborhood into this branch, if you take the entire neighborhood into the entire neighborhood, you somehow like delete one T fraction of a balanced separator. Yeah, that's the intuition. But it's hard to measure, okay, what does it mean? Okay, you delete one T fraction, but then another balanced separator came in the next step. What's happened? And these buckets, as we showed, shrink these buckets, the size of these buckets will be like an excellent measure how the algorithm progresses, or how the algorithm disconnects the graph, yeah? So the intuition, like, let me repeat this intuition. The intuition here, I will put in the corner, I have got this graph G, and there's this balanced separator, which is like a neighborhood. I will make it green. There's a balanced separator, which is neighborhood of T vertices on the path, okay? And the intuition is that you choose one vertex from this path, and you branch in this G minus V and G minus neighborhood of V. And the intuition is that in this branch here, you delete the neighborhood of this V, and this should be a substantial progress because you delete a constant fraction, one T, think T constant, of a balanced separator in a graph. That should be a good progress, but how to measure it? And the crucial observation is that the buckets, the size of the buckets is the correct way of measuring the progress here, okay? So let's do it the following. Let's think of the following. Okay, so this is all the bucket, and I want to say the following. I want to say the following, that in PT3 graph, so let me write the lemma. If G is PT3 and connected, then there's a vertex such that N of V hits 1/2 fraction of paths in 1/2T buckets. Yeah, so there are n choose 2 buckets. And I want to say that there's a vertex that for 1/2T fraction of our buckets, yeah, 1/2 like n choose 2 buckets, for like n 1/2T fraction of buckets hits a constant fraction of the guys there. Okay, and this lemma is actually pretty obvious. Let's prove it. Let's take this balanced separator. So this is the graph G. There is the path x of size at most less than T actually. Okay, and this is the neighborhood, such that n of x, g minus n of x has connected components of size at most n half. Okay, so they're less than half up there. And now look that n of x intersects, hits, I mean hits mean intersects, hits all paths in at least half of the buckets. Yeah, think the following: if you choose randomly a pair of vertices, so let's take a pink color. If you choose randomly a pair UV, with probability more than half or at least half, it won't land. It won't land in the same connected component. It won't land in the same connected component of g minus n of x. Yeah, I mean it won't land in the same connected component of g minus n of x, which means that at least half of the pairs, are disconnected by the n of x. And there's a crucial observation if you go back up there, is that bucket is non-empty if and only if u and v are the same connected. Yeah. Yes, if two guys are connected, there's actually an induced path between them. If they're in different connected components, there's no induced path between them. That's the obvious thing. And now the point. Now the point is that here, if you delete this neighborhood of t vertices or less than t vertices, then you disconnect like more than half of the pairs of vertices. So you hit everything in all the buckets, everything in at least half of the buckets. Okay. But there are at most t vertices here. Which means that actually there is a red vertex. That hits like 1 over t part in like 1 over 2t buckets. Yeah. So there is actually like a x in x. So the n of x hits 1 over t paths in 1 over 2t times n choose 2 buckets. Okay, so there's actually, I mean, because t vertices hit all the paths in half of the buckets, there's one vertex that hits, whose neighborhood hits 1 over t paths in 1 over 2t of the buckets. Okay, I mean, actually put 2t here and here. Actually, like I could remove 1 to here up there. Okay, so this is like the lemma, and this is the measure of the progress. Yeah, so let's think what happens. Let us see what happens. I want to choose this vertex as my branching pivot. This is my vertex I want to branch on. Okay, I mean this is like sort of heavy vertex. Its neighborhood hits a lot of paths in a lot of buckets. Okay, so now let's see what happens in the recursion. So what I'm doing here in the algorithm, just to make it clear, I'm looking at all these buckets and I'm hitting. I'm looking at all these buckets and I'm hitting. I'm taking as a pivot a vertex that hits a lot of paths from a lot of buckets. Okay, I have guaranteed that this vertex exists. And the important part now, I mean, we used PT-freeness to prove that this guy exists because we used the alpha path argument. But there's a second part that I'm now silently using here, is that I can actually look at all these buckets. This bucket is of size at most n to the t, because the induced paths are of length at most t. So this bucket is really small, it's of size n to the t, which means that I can look at it, enumerate it, and just like look at every vertex and see how many paths it really hits. Okay, I can look how many paths this neighborhood of this vertex hits. And now let's do the complexity analysis of this algorithm. Okay, yeah. So I start with the graph G and I choose some vertex V and I branch delete V or delete the neighborhood of V. Okay, and then I branch and branch. And let's call this as a failure branch and this is a success branch. Why do I call success branch? Because I get some significant progress. In this branch, a constant fraction of buckets gets decreased by 1 minus, I mean, 2t or 2 by a constant fraction. Okay, so if you think about the following, if you have got this n choose 2 buckets, I will now draw buckets. If you choose n to choose 2 buckets, and now a constant fraction of the buckets gets shrunk by a constant fraction, okay, and they are initially of size n to the t. They're initially of size n to the t, and they can shrunk. They shrunk by a constant fraction. Constant fraction of them shrinks by a constant factor. This can happen only log square n times. I mean, this is like something you need to stir for a while and use your secret knowledge from discrete mathematics for first year. But if you have got like n square objects, each of size, a polynomial number of objects, and each object is of polynomial size, and at every step you shrink a constant fraction of them by a constant fraction, this can happen only log square n times. Yeah, in a sense that there's one log for like shrinking and one log for shrinking the space in this dimension.
What isn't it just log n?
No, because you shrink a non-empty buckets. I mean, in a sense, you shrink a constant fraction of non-empty buckets, but because
Okay,
there's another.
I thought that you assume that you always shrink. Okay, so you shrink a constant fraction in a constant fraction of buckets.
Yeah, because that's a good question. I mean, I'm a bit like hand waving here. The question what you're saying here is that I'm not shrinking like 1/2t, and I'm assuming the graph is connected here. So there's like a moment when the graph becomes disconnected, and this boils down really that I'm always like shrinking, like this fraction of the buckets I'm shrinking is the fraction of the non-empty buckets. So like as the graph shrinks, the bucket, if the bucket becomes empty, that means that I disconnected something, and then this 1/2t is applied to connected components. So like it's 1/2t of non-empty buckets really, of non-empty buckets here. Okay, so what I'm doing, but the complexity analysis boils down to the fact that if you have got like polynomial number of buckets and every bucket is of polynomial size, and then one step you take a constant fraction of non-empty buckets and shrink it by a constant fraction, then you can do it only for log square n times. And one log comes from like shrinking in this dimension, and one log from shrinking like the number of non-empty buckets in this thing. Okay, and now so this is the complexity analysis here. I mean, I hand wave it a bit. If you write it formally, you need to write some potential, but this is the intuition. So in this tree, however you go only log square n times in the like success direction. So this is like a very skewed tree, and it has got size n to the order of log square n by this fact. Okay, so that's it. And that's the end. I mean, barring some details of complexity analysis, if you want to really like make it formal, I mean, it takes like 1 page more really to make it formal. And this is it. And this is the n to the order of log square n time algorithm for maximum weight independent set in PT3 graphs.
I think it's at this point maybe to see that this recursion tree has size n to the order of log square. You can think of it as the depth of the recursion tree is at most n, because every time you remove one vertex, and you have at most log square n success branches on a branch. Yeah? So the number of possible branches in this tree is at most n choose log square n. Yeah, so this is a concise argument to say that this branching, the whole branching tree has quasi-polynomial size. Mm-hmm.
Okay.
Yeah.
Okay, so that's what I want to show you on the slide. Let me go to the slides back. Okay, so
can I have a question?
Mm-hmm.
So is it correct that if somebody was able to prove that this was shrinking faster somehow, these buckets, than log n, then this would immediately improve the running time
yeah,
of
but
the
I
algorithm?
don't think it shrinks faster.
Yes, but maybe you can do something like slightly different. I don't know.
Maybe you can. I don't know how to do it.
Like this thing we came up in July, right? So it's a really fresh thing. You probably can tinker with it a lot and improve various things. Yeah.
Okay. Okay. So I present you PT3 graphs. If you think about C more than T3 graphs, actually it's not easy, because I used PT3ness twice. I use PT3ness to have the balance separator to say that there is a guy using constant fraction of every thing, but I also use this fact to say that every bucket is small and of size n to the t. And this was important because I mean the number of steps I'm shrinking a bucket is like log of the size of the bucket. So not only is it important to enumerate it, to know which vertex to branch on, but also like the number of steps to shrink one bucket to be empty is like log of its size. And in C more than T3 graphs, you don't have any guarantee how many induced paths are between two vertices. They can be exponential. I think so. At least I don't see an argument why it's not exponential. Yeah. So this actually becomes more complicated in the in this graph. So like one way we use PT3 graphs doesn't generalize easily to C more than T3 graphs. And actually, it was that like while we were working on the PT3 graphs, and we realized the simple algorithm just before, because the algorithm of Peter and Daniel was a bit more complicated. At the same time, Peter and Daniel posted an n to the log to the 5 algorithm for C more than T3 graphs. So like one more log than on the slide. And we thought for a while, okay, they were based on their own approach for PT3 graphs with a few new combinatorial insights. So we thought for a while how much we can use our own combinatorial ideas with their combinatorial ideas to get it together for C more than T3 graphs, and they're actually doable. There's one log less, similarly, there's one log less was there before. And yeah, so there's an algorithm there. This like essentially now, I mean, they posted on Archive, then we posted our way on Archive, and this will be like a joint paper soon. I mean, this thing is already on Archive in 2 parts. So there's the algorithm, then our algorithm on Archive, but it's already up there. What we have already written but not put on Archive was that actually, okay, so this is one direction you can go to C more than T3 graphs, okay? You can go to C more than T3 graphs. The other direction is that, okay, we did maximum weight independent set. What about free coloring? So the point is that free coloring is only slightly more complicated than maximum weight independent set. The branching is slightly more complicated. You're branching whether this guy gets this color or not, and this type of objects. This is known, and there's not much more. I mean, the free coloring has got exactly the same complexity as maximum weight independent set. It's slightly more complicated branching. But you can also ask the question about feedback vertex set. And feedback vertex set is a bit more complicated because you cannot just take a vertex and delete its neighbor. If you take a vertex, you can delete its neighborhood. Maybe you took a vertex which has a high degree in your final tree, and when you think of feedback vertex set as actually like maximum induced forest, yeah, the dual version. It has high degree there, and maybe it's actually and maybe yeah, and maybe it's high degree, so maybe you cannot easily like discard the neighborhoods. That seems quite complicated. And yeah, so actually we knew how to do it in PT3 graphs, and also Peter and Daniel knew how to do it in PT3 graphs, so we merged. And there's like a sort of like heuristic that if you can do independent set, if you can do feedback vertex set, then probably you can do constant tree width and keep any MSO formula on this constant tree width. So what's really like, the result is that in this quasi-polynomial-time, you can find a maximum weight induced subgraph that has got some tree width bound and satisfies some MSO, so your favorite MSO2 property when K is constant here. Yeah, the T and K and the formula, the MSO property is constant here. Okay. This one is already written down. We have got a manuscript here, but it's not put anywhere, so it will, because it's waiting for the next bullet that will appear here in a moment. So now, okay, there's the dimension of C more than T3 graphs, and there's the dimension of PT3 graphs, and yes, it can be merged. It can be merged. There's like some log loss in the exponent because actually in the PT3 graphs, the thing that you can rely a lot is that bounded tree width and PT3 means bounded tree depth, and that makes your life a lot easier in a few places. With C more than T3 graphs, it's no longer true. And I think we are quite convinced that it will be actually log to the 5, but just for safety, I put higher exponent here. But there's some question now, and it's being written down, so I'm quite confident to like put it here because I mean we are already advanced in writing it down. It should appear on Archive within 2 or 3 weeks, I would say, unless something will break down, and then I will apologize a lot. Good. But this is like the directions we know how to go, or think we know how to go. We have got no clue how to get rid of any log there, and if in particular go to polynomial time, but this log to the square seems like, okay, we don't know how to improve it. The algorithm seems now pretty simple, and we don't know really how to improve it. And we don't know how to go for subdivided close. So we work with PT3 graphs. The generalization to like long haul free graphs, C more than T3 graphs, was already quite complicated. And if you look at the QP-TAS, as I said before, the QP-TAS actually worked for subdivided close free, and it was like ratio 1 to 10 or 1 to 20 between the complexity of PT3 graphs and subdivided close free graphs. So here we don't know. I mean, there are of course some ideas, some intuitions for QP-TAS in which direction to go, but this seems like highly open how to do quasi-polynomial algorithm there. Yeah, so that's like the 2 directions we really don't know how to do, and it doesn't seem like the answer is just around the corner. It seems like the answer is behind 500 corners. Okay, and I think that's it. I want just to give a hat tip here to Terka, who from her I took the first few slides. I think this is like a third, fourth, or fifth generation of these slides, starting from her talk on some old P63 or P53 graph algorithms, and I'm just reused the introductory slides of Terka. Thanks. So I think I'm done here, and we take any questions. I will go back to the slide. Maybe it's better.
Can I have a question?
Mm-hmm.
So these fewer logs in the exponent, does it relate only to this n to the power log square n for PT3 graphs, or also n to log to the power of 4 for...
So we don't know how to make it better with the C4, this 4, and while the algorithm for PT3 graphs was very clean, and in a sense, I mean, you need to have got some really nice new insight to get better log. I think so. Then this log to the 4, I mean, I'm not completely satisfied with how we do C more than T3 graphs. I mean, it works, but there's like 2 levels of recursion. There's like 1 level of objects you hit, not paths, but like tripods. Then if you cannot hit them, you change this branching strategy to a different one, and you prove that if you end the different one and go back, you're in much better shape for the primary one. And it's more complicated than I would hope for. So maybe shaving off log to the 4 in C more than T3 graphs is more achievable thing. And maybe a better understanding of what the actual algorithm now do is like better, because this log to the 4 is really like the combinatorial ideas of Peter and Daniel merged with our like path hitting approach. And maybe this log, I mean, we don't know how to shave this log, but I will be like, it may be easier to shave off log here.
Yeah, we seem to be not having the clue of how to shape this log square in PT3. The other logs probably with better understanding of the measure of progress.
So are you working on this currently, or is it like somehow not being worked on?
So I mean, I can say for myself, at the moment I'm writing down the first bullet.
Yeah. So
actually, I was typing it the hour before. I mean, at least 1 hour before the seminar, I was spent the last hour before the seminar typing the first bullet.
Yeah. So we are now working on getting these results down, and then maybe once they are submitted, we will think about the further proceedings.
On my side, there was no substantial thinking on neither of the direction.
Good. Any more questions?
Just out of curiosity, do you have any graphs where your algorithm works in an exponential log square time?
No, okay. I don't know. I mean, I haven't really constructed anything. Like
I don't think that we.
It's really hard to draw a PT3 graph, complicated PT3 graph.
Exactly. Yeah, it may be that with a clever choice of pivots, you can actually make this branching polynomial time. This would be consistent with our knowledge. It's just that at this point we have a quite a surprising measure of progress, which is the number of those paths in those buckets, which certify that that with a clever definition of a pivot, you can do quasi-polynomial branching.
Okay, thank you.
Okay, so but are there any other algorithms? Because this one is based on just choosing the pivot and branching on the pivot, but are there maybe some other algorithms?
I mean, the approach to get polynomial time algorithms for P5 and P60 graphs is very different. It's a dynamic programming algorithm, not like carefully chosen objects. But yeah, I mean, but yep, but that's but I don't think there's anything else really.
Yes, but that's only for T constant, like up to 6.
That we know how to make it work up to 6 equals 6.
Okay.
So the intuition, at least for me, is that essentially when you are turning a quasi-polynomial time algorithm into a polynomial time algorithm, you should stop thinking about recursion and start thinking about dynamic programming. So maybe with this kind of an understanding, there is like a polynomial size family of objects on which you can do a DP. And this could work, meaning this is how it works with P5 and P6 and these objects are potential maximal clicks. But at this point, we have no clue how to approach turning this branching into a dynamic programming over suitably defined objects. Okay, any more questions?
I think there is a question of Carol on the chat.
Oh, really? Okay.
So in the C more than T3 graphs, I think there's some polynomial in T.
Yeah.
I mean, there's some polynomial in T in the exponent. For MSO, I don't answer this question because
yeah, so for MSO, yes, you are essentially either guessing some run of an automaton over some small subtree, small being exponential size, or getting some MSO type. So you will get in this O notation in front of this logs a factor that depends on the formula.
Yeah, I think also like the original paper of the of Fox, they analyzed in this like T cube or something like that, or T to the 4 in their algorithm, or T squared, I don't remember. And I think we stopped analyzing it, but I think we get rid of one log, but we added 1 or 2 more T's in the exponent. But I mean, it's still polynomial in T there.
Yes. Any more questions? We have quite a number of questions today.
Okay, I have no more questions, but I just wanted to say that this is a very, very nice result.
Oh, thank you very much. We are also very happy with how clean this argument is at the end of the day. So I just wanted to point out that this was open for like 20 years, whether it can be close to polynomial. And the argument that we just showed you, it is very much based on our understanding of what Peter Gartland and Danielowski did. When you look at the two papers, the argument superficially looks very different, but this is based on understanding what they actually did. Okay, good. So if there are no more questions, then maybe we can slowly converge to the end.
I'm stopping the recording.
Okay.